Hi guys, we will be discussing this problem called eight neighbors. So the description reads as the following. You can go over the description, but I would like to um, like go over the problem statement in a clearer way on this slide. Okay, so let's take two sample examples, input examples. So the first thing that we are getting for a particular so there are two test cases. For the first test case, we are given the size of the matrix, that is 3 by 3, and the matrix is of containing of two characters only, x and dot. And what we are asked is, on top of this matrix, we are also given a um, cell with x and y coordinates uh, in one based indexing. So that pertains to this red dot here, that is 2, 2. And for the given coordinate, we need to answer that whether all the characters, all the eight neighbors of this particular cell, all of them are x or not, right? Um, so that's the problem statement. So we are given a cell, we are given a character matrix containing x and dot, and for the given cell coordinate, sorry, for the given cell, we are asked that are all the eight neighbors, uh, all of them have x as the characters in these entries, right? And what are the eight neighbors? So we will be going over that. So let's imagine we are standing at some arbitrary index ij, and the eight neighbors are these type of cells. First categories are the non-diagonal neighbors, and the second category are the diagonal neighbors. So had the question been for four neighbors, then generally depends on problem to problem, but generally it is meant that they are asking for the non-diagonal neighbors, right? But in this question, we are asked about the eight neighbors of that particular cell. So these are the two types of neighbors, right? Um, and imagine, so generally the notation is the following: 0, 0 is the top left corner, and the columns will run in the horizontal way, and the rows will run in the vertical way. And therefore, um, you can figure out we can figure out the let's say I is a iterator on running on the rows, j is an iterator running on the columns. Then for this arbitrary cell ij, if we move upward, we are essentially subtracting one from the row, and the column stay as it is. And if we are moving to the left of that cell, so that means we are staying at that row, but the column we are decrementing by one. Right? And similar arguments you can follow for each of them, and you can quickly um, figure out the neighboring cells in this manner. And for diagonal elements, they are always either incremented or decremented. Sorry, either incremented or decremented by one. Both the coordinates, right? Um, so therefore, when we are moving in that direction, it essentially means we need to visualize this we need to visualize this diagram in order to answer this. So if we are moving in so what is this? This is west and south. So southwest direction. Um, then we are essentially subtracting one row, but in the column iterator, we are incrementing it by one, right? So similar arguments we can give for all these four coordinates, all these four neighbors, right? Um, and therefore, all it boils down to is these eight type of neighbors, right? And that is the definition of eight neighbor throughout the question. So let's take this example. As we can see, this is in example one, and here it actually have like all the eight numbers neighbors actually have um, x in it. So the answer to this will be yes. And if we look at this, the input cell is 2 2, and that's essentially the same cell as the above. And we do not care whatever is present in that cell. All we care about is the neighboring elements, right? All of them are fine except for this last pair, right? So this coordinate will be 3 3. So except for this 3 3, all of the rest have x in their entries. Um, so therefore, the answer to this will be no. So that's the problem statement. Um, and let's look at how we can implement this, and you can learn about this trick because this trick will come in handy in many grid-based questions in graph. Um, so it comes in handy. So so basically, so generally people write it as dx and dy. You can write it that way as well, but I generally prefer to write it as di and dj, so that I have the notation of I and j. I is always running across the rows and j will run across the columns. And this one we can quickly um, fill it up, just recalling and visualizing in our mind. Okay, let's go in that direction, and then let's go in that direction, then let's go in that direction, so on and so forth. And so if we are moving upwards, we know that the row will stay as it is, but the apologies. So the row will be decremented by 1 and the column will stay as it was. So I minus 1 j, right? So that means for that arbitrary I and j, we are essentially decrementing it by 1 and doing nothing to the column, right? So minus 1 and 0 is the encoding for that direction. And if we are going in this direction, let's make it green. If we are going in this green direction, then the row will be decremented by 1 again, but column now will be incremented by 1. So we can encode it as minus 1 and plus 1, right? These are the contributions to those respective directions. Um, and then for this blue direction, let's make it blue. Here the row stays as it is, so therefore I, but j will be incremented by, right? And therefore it can be encoded as 0 and plus 1, right? And so you can fill this entire di and dj this way. Just visualize the direction, put the encoding. Visualize the direction, put the encoding, so on and so forth. As you practice this a lot in your mind, it will come in, uh, it will basically be second nature. So, yeah, so ensure practicing this, like populating this array a lot of times. Okay, so now for asking for a given cell, how we will figure out the new I and new j, right? Um, that's what the definition that we have just come up with. That okay, whatever your fixed I be, how much should I contribute? Well, ID is the idth direction. ID here means some. index of this array, uh, I mean the respective indexes of these arrays, di and dj, they will always have the same id values, right? Because that's how we have populated this. That's a fixed direction. So, that's what we are saying that okay, it fixes the cell coordinates of the idth direction. Okay, and these ones will be the new I and new j, and there will be eight directions. So ID will run 0 all the way through 7. Okay, so then what will be the final algorithm? Well, we can just iterate over this using a for loop. We will see the code in a while, but imagine for a given input cell ij, all we need to do is iterate the entire array um, and basically maintain a flag or something that will tell us that all of them x, or there exists some of which is not x, which is basically a dot. Okay, and because we are doing this um, exactly, there will be eight computations, right? There will be exactly eight checks, which is a constant number. So the complexity of this will be order one, right? Order one per test case. So let's go over the code. So okay, first we will take the input of n and m. We make a character array. We take the input, and this OK variable will tell me for the given xy, uh, the cell of interest, are all the eight neighbors uh, containing x or not. So for that, because we have taken it as zero based and the input will come in one based indexing, we need to ensure that these are also made to zero based. It's for just implementation convenience. Okay, and then we just populate the di and dj arrays, and for a fixed idth direction, um, we figure out the new I and new j. And now one important thing to note here is we have to check that okay, is it valid? That is it within the bounds of the matrix, or is it going beyond the bounds? Right? So as you can see here, the max number of rows will be what will be the coordinate I minus one, and the max coordinate of the column will be j minus one, and min of them will be 0 0 for both of them. So that's what we need to check. Even after figuring out the new I and new j, they need to qualify the validity. That is, these are valid coordinates. So that's what we have written as I have just explained. Um, Once it is valid, then we need to ask the question that is the entry dot? If the entry is dot, we can just make OK equal to false, and that is sufficient enough to say no, right? Um, Else, if it never falls into this, that is, all of the valid neighboring indices, all the valid eight neighbor coordinates or cells are x's. Then we will never go through this basically scope, and finally it will be yes, and otherwise it will be no. That's the simple algorithm, and as you can see, this loop is constant. That is, there will be exactly eight iterations no matter what, and eight is a constant number, so order one will be